Hi students, have a nice day. In this section we are going to discuss about the hybridization involving d orbitals. The elements present in the third period contains d orbitals in addition to the s and p orbital. For example, phosphorus. The electronic configuration of phosphorus is the valence shell 3s2 3p 3 3d 0. Okay, d orbital is there. There is no electron, but d is there. And also d orbitals having comparable energy with the 3s and 3p. Are you clear? The third shell contains 3s, 3p and 3d orbitals. That 3d orbitals having comparable energy with the 3s and 3p. Similarly, the 3d orbital having comparable energy with the 4s and 4p orbitals. Okay, as consequence, the d orbitals involving hybridization, 3s, 3p, 3d orbitals or 3d 4s, 4p orbital. The hybridization involving 3s, 3p, 3d or 3d, 4s, 4p orbitals are possible. Let's discuss some examples. Okay, the first one is the hybridization is dsp2 hybridization. In this case, 3d orbital, the 4s orbital and 4p orbitals are involving hybridization. Okay, the hybridization is dsp2. The example for this hybridization NiCN 4 times 2 minus. It's a complex. Okay, NiCN 4 times 2 minus a complex, and the shape of the complex is square planar. What is the shape of the complex? It is square planar. So in this case, the orbital involving hybridization is 3d, 4s and 4p. Remember that. Next is sp3 dehybridization. Example, PF5, PCl5 and the shape is trigonal bipyramidal. Trigonal bipyramidal. The shape of the molecule is trigonal bipyramidal. And the other one, okay, dsp3. Okay, dsp3, the molecule is brf5. Okay, brf5. The another example is xeof4. And the shape of the molecule is square planar. Square pyramidal. Square pyramidal. Square planar, dsp2 hybridization, dsp3 hybridization, square pyramidal. Not bipyramidal, square pyramidal. Okay, in this case, inner d orbitals, if we write d earlier or in the first, we understand that the d orbitals is taken from the inner shell. Okay. So dsp3. Okay, what is the shape of the molecule? It is square pyramidal. Examples are brf5, xeof4. Okay, xenon oxyfluoride. Next is sp3d2. Okay, sp3d2. The example is SF6. SF6 6 is an example. The shape is octahedral. Okay, the shape of the molecule is octahedral. Another example is CrF6 3-. It's a complex. Hexafluorochromium 3 ion. Okay, it is a complex. Later you will study in the plus 2 classes coordination compounds. Another hybridization is D2sp3. Okay, D2sp3. In this case, inner d orbitals participate in the hybridization. Remember that D2sp3 means inner d orbitals participated in the hybridization. Are you clear? And the example is FeCl 6 times 3-, or NiCN 6 times 4-. Okay, and the shape is same, octahedral. Many examples are there. Okay, many examples. Here one more example is CONH3 6 times 3+. Okay, so many examples in the case of sp3d2 and d2sp3. So once again, the d orbitals participating in the hybridization, either inner d orbitals or outer d orbital is taking. If the inner d orbital is taking for hybridization or participating in hybridization, we can say that it is dsp2, dsp3, d2sp3. Inner d orbital is taken. If the outer shell or valence shell orbital is taken, we can write that sp3d, sp3d2 like that. Are you clear? Yes. Let's discuss some examples. The hybridization involving d orbitals. First one is formation of PCl5 molecule. PCl5 molecule, phosphorus pentachloride, and the hybridization is sp3d. Okay, let's discuss how the PCl5 molecule is forming. PCl5 sp3d hybridization. First of all, we have to write the ground electronic configuration, ground state electronic configuration of phosphorus. Valence shell 3s2, 3p3, 3d0. And let's discuss the representation. S electrons 2. Okay. P electrons 3. There are 2 s electron and a 3 p electron. Phosphorus in the excited state. What is excited state? The atom is excited by attaining some energy, or the electron is excited from lower orbital into the higher orbital, or lower shell into the higher shells. So here this electron is transferred into or jumped into the d orbitals. Now the electronic configuration of phosphorus is 3s1, 3p3 and 3d1. Okay, so 1, 2, 3, 4, 5. 5 electrons. The 5 electrons are distributed in s, 3p and 3d orbital. Are you clear? Yes. Then by involving the hybridization, 1s, 3p and 1d orbitals. What is hybridization? Intermixing of atomic orbital the hybridization is sp3. Okay, what is the hybridization? The hybridization is sp3. After the hybridization, we know that the orbitals having identical shape and equivalent energy. Okay, the orbitals having identical shape and equivalent energy. And the remaining 4 orbitals is there. Okay, it is 3D orbital. This one is sp3d. This one is sp3d orbital. Then what is the shape of the molecule? We know that the shape of the molecule is trigonal bipyramidal. Okay, 3 hybridized orbitals are in the equivalent position. Okay, equivalent position. One is above the plane, the other is below the plane. Okay. One is above the plane, the other is below the plane. Each orbital having electron. And this orbital overlap with the p orbital of the, chlorine atom. Okay. Here the chlorine atom valence shell electronic configuration 3s2, 3p5. One of the p orbital is unshared. S 2 electrons, P 1, 2, 3, 4, 5. One of the p orbital contains half filled or single electron. That orbitals comes for the bond formation. This is chlorine atom and the bond is shared. Here also another chlorine comes, share the electron. Here also another chlorine comes and share the electron. Here also another chlorine comes and share the electron. These are chlorine atom. And here the chlorine comes and the p orbital is overlapped. Are you clear? Yes. Then phosphorus is at the center. Phosphorus undergoing hybridization. Phosphorus is in the center. Then let's draw the shape of the molecule. It is trigonal bipyramidal. Phosphorus, then 3 chlorine atom in the same plane. Are you clear? 3 chlorine atom in the same plane. One chlorine is above the plane and the other chlorine is below the plane. That's why I put dotted lines up to here. Then we can see that. Okay? Yes. Then the bond angle is 120 degree. Equatorial bond angle is 120 degree. You remember that. Equatorial bond angle is 120 degree. All the equatorial bond angle is 120 degree. And the axial bond is 90 degree. Okay, axial bond is 90 degree. So, by joining these points, we get one pyramid above the plane. One pyramid above the plane, the other pyramid below the plane. So, what is the shape of the molecule? Trigonal bipyramidal. Okay, trigonal bipyramidal. Trigonal bipyramidal. Are you clear? Yes. Then another important thing we have to discuss. PCl5 molecule is reactive. Why PCl5 molecule is reactive? The answer is in PCl5 molecule there is two type of bonds, equatorial bonds and axial bonds. The 3 chlorine atom in the same plane and is in the corners of an equivalent triangle is called the equatorial chlorine atoms. These are lie in 120 angle. one chlorine is above the plane, other chlorine is below the plane. The equatorial chlorine repel the axial chlorine. Okay, listen. The equatorial chlorine atoms repel the axial chlorine atom. So axial bond is longer than equatorial bond. Once again, due to the repulsion of equatorial chlorine atoms, 3 equatorial chlorine atoms, axial bond is elongated. The length of the axial bond is more than that of the length of the equatorial bond. One is above, the other is below. What happens when bond length increases? Bond length increases, bond strength or bond enthalpy decreases. Bond dissociation enthalpy decreases. Hence, PCl5 molecule is reactive. It's a very important question. Why PCl5 molecule is reactive? In PCl5, 3 chlorine atoms lie in the equatorial position and 1 chlorine is above, the other in the below. Equatorial chlorine repels the axial chlorine atom. Due to this repulsion, to attain stability, the axial chlorine is elongated. The axial bond is elongated. Elongated means length increases. Okay, bond length increases. So when bond length increases, bond strength decreases, and hence the bond dissociation enthalpy is low. And that's why PCl5 molecule is reactive. It's a very important thing. Also in a solid state, PCl5 molecule exists in the PCl4 plus and PCl6 minus in the solid state. Remember that. In solid state, PCl5 is exists as PCl4 plus PCl6 minus. This is tetrahedral and the other is octahedral. Tetrahedra and octahedra are joined in the solid state. Okay, next we discuss about the hybridization in sulfur atom. sp3d2 hybridization. Formation of SF6 molecule. Okay, formation of SF6 molecule. SF6. sp3d2 hybridization. sp3d2 hybridization. Sulfur atom in the ground state, 3s2, 3p4, 3d0. Sulfur is the element which is present in the third period. The electronic configuration, valence electronic configuration is 3s2, 3p4, 3d0. Represented in the orbital. S2 electrons, P 4 electrons, and d orbitals empty. The orbital is there, but the orbital is empty. Sulfur in the excited state. What is excited? The electron is jumped from lower level to the or lower energy level to the higher energy level. Here, one of the s electron is jumped into the d orbital. It is paired and this electron is moved. And in the another p electron also move into the d orbitals. Now the electronic configuration, the excited state electronic configuration is excited state. Sulfur is in the excited state. Sulfur excited. Gs means ground state. Es means excited state. One electron in the s orbital and 3 electrons in the p orbital. 2 electrons jump into the d orbital from s and p orbital. Now the electronic configuration 3s1, 3p3, 3d2. Are clear? Yes. 3s1, 3p3, 3d2. S. Now 1s, 3p and 2d orbitals undergoing hybridization. The hybridization is sp3d2. Hybridization is sp3d2. Are you clear? Yes. Then after the hybridization, the energy of hybridized orbital is same. Similarly, they have identical shape. After the hybridization, hybridized orbital having identical shapes and equivalent energy. You remember that. How many electrons? 1, 2, 3, 4, 5, 6. So 6 electrons are present in the sp3d2 hybridized orbital. Then how the 6 orbitals oriented? It is oriented in the coordinates of an octahedra, sulfur. Okay, sulfur. One sp3d2, another sp3d2, another sp3d2, another sp3d2. One is above the plane. Okay, it's a square. And one is above the plane, the other is below the plane. Okay, up to that you put dotted lines. And then below the plane, you can draw a thick line. Each orbital contains one electron. So there are 6 electrons. 1, 2, 3, 4, 5, 6. Are you clear? Yes. Then F atom, fluorine atom. Fluorine having the electronic configuration 2s2, 2p5. 2s2, 2p5. Then s orbital 2 electrons. P orbital 5 electrons. 1, 2, 3, 4, 5. Okay. One of the orbital is singly occupied. Yes. Then these p orbitals coming for overlapping. What is overlapping? Interpenetration. Then overlapping, one SF bond is formed, the second SF bond is formed, the third SF bond is formed, the fourth SF bond is formed, fifth SF orbital is overlapped. Okay. Then last one is the sixth orbital is overlapped. And what is the shape of the molecule? The shape of the molecule is octahedral. Sulfur in the center of octahedra. Fluorine, 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 fluorine. One fluorine is above the plane. The second fluorine is below the plane. By joining the apexes, we get octahedra. Okay, the square by joining the four corner into one point, one apex, the other below. It is not a square bipyramidal. Okay, you don't think like that, because all the bond length and the bond angles are 90 degree. The bond angle is 90 degree. This bond angle is also 90 degree. The bond length and the bond angles are same. And it is not a square bipyramidal. Somebody usually asking, sir, is it a square pyramid? In the case of PCl5, it is a trigonal bipyramidal. Here also the repulsion is there. Yes, repulsion is there. But all the bond length are same and the bond angle is same. In the case of PCl5, equatorial bond angle is 120, axial bond angle is 90 degree. Okay, when 90 degree comes, the repulsion is more. So in PCl5 the shape is trigonal bipyramidal. But in the case of SF6, the bond angle 90 degree and the shape of the molecule is octahedral. Okay. If the orbital is chosen from the inner shell D2sp3, it is also octahedral. But DsP2 is square planar. DsP3 is square pyramid. In the case of BRF5, the shape is square pyramidal. The hybridization is DsP3. Okay, are you clear? So you practice the hybridizations. Hybridization is a very important concept in VB theory. Overlapping of orbitals. Also hybridization. Hybridization is intermixing. Overlapping is interpenetration. That's the difference. Overlapping is interpenetration of orbitals. Hybridization is intermixing. Even though this theory has some drawbacks. Okay, while VSEPA theory has some drawbacks. Similarly, VB theory, valence bond theory has some drawbacks. So these drawbacks are corrected by modern theory, molecular orbital theory. In the next section, we will discuss AMO theory. Okay, molecular orbital theory. It is shortly called or known as MO theory. Thank you.